This is a lesson on related rates. Yesterday we did implicit differentiation, and it rolls right into this section. So yesterday we differentiated equations with respect to x. So let's think about it. When I differentiated y squared with respect to x, I got 2y dy dx. So I can differentiate any variable with respect to another variable as long as I include this part in here. Now if I differentiate y with respects to y, I don't have to do this. So I can, down here in these related rates, these are all areas of spheres and volumes and formulas. I can differentiate every one of these with respects to time. I just have to put d whatever variable over dt. So we go, remember that pi is not a variable, it's a constant. So the derivative of a, any variable, is 1, and then we put dA dt. Then 4 pi times 2 r to the first dr dt. So what each rate is, this is the rate of the area, the rate of change, could be increase, could be decrease, of the area of a sphere over time. Whether it's a balloon that it gets stuck in the refrigerator, what happens is those molecules inside shrink, so it would be, something like that. This is the rate of the radius changing over time. Alright, same thing, dv dt. 3 times 3, that goes away. 4 pi r squared dr dt. Here's one. This would be like a Pythagorean theorem solved for a. Well, let's simplify this. C is a constant. I'm going to square both sides. There's nothing wrong with that. It's still the same. Alright, so C is a constant. So we go, derivative of 2a squared is 2a dA over dt. The derivative of any constant is 0, then minus 2b dB dt. Right. R is a constant, so we don't have to worry about R. If R was not a constant, we would have to use the product rule. So dV dt equals 2 pi, oh no, I'm sorry, R is a constant, so equals pi r squared, derivative of h is 1, dh dt. Derivative of cosine is sine theta, and then we took the derivative of the inside, which was theta, which is 1, so d theta dt equals, this is 1 over 15x, so 1 over 15, the derivative of x is 1, dx dt. This would be pulling this ladder away from this wall, how these angles are changing. And then the last one, volume of a cone. Now we do have two variables in here, so we're going to have to use the product rule. dV dt equals 1/3 pi. Derivative of r squared is 2r times h dr dt plus r squared, derivative of h is dh dt. Alright, you can do that. You can do related rates and understand what these rates are. This is the change of the volume over time. This is the change of the radius over time. This is the change of height over time. application problems. So air is leaking of inflated balloon of the sphere with the rate of 230 pi cubic centimeters per minute. At the instant where the radius is 4 centimeters, what is the rate of change in the radius of the balloon? So we're talking about the volume of a sphere. Alright, so we need to make sure that we have variables. I've got radius, I've got a radius. I've got one rate, I'm going to have two rates. And so we're looking for the third rate. So radius is 4. This is the amount of air leaving, so it's the and it's leaking out, so this is negative. To the 30, that's it. Okay, and then we're looking for dr dt, the rate of change of the radius of the balloon, the rate of change of the radius of the balloon, rate of change of the radius over the balloon with respect to time. So we've already identified all the variables up there. So now we take this and implicitly differentiate dv dt equals 4 pi r squared dr dt. Plugging in all our variables, dv negative 230 pi equals 4 pi r, in this case is 16. So we divide 4 pi 16, pi's will cancel. 230 divided by 4 divided by 16. Where is my calculator? And I get that. So, and this equals to dr equals negative 115 over 32, and this is leaking out, radius is cubic centimeters, so centimeters per minute. And that's all you have to do. Find the formula, take the derivative of that one again. Stone is dropped, so that stone hits the water right there. It's going to create a ripple. It's going to create a ripple. It's going to create a... So this radius is ever increasing, which also increases this area. So the radius is increasing about 1 foot per second. When the radius is 4 feet, what is the rate of change of the area? So area equals A equals area, R equals the radius, dA dt is the rate of change of area, change in area over time, and dr dt is the rate of change of radius over time. So we take here, it's given us, alright, so what variables have they given us? They're going to want us to put into 4 after we differentiate. The rate of dr, the radius is increasing at the rate of 1 foot per second, so A equals pi r squared dA dt equals pi times 2 times r dr dt. Now we plug in what we know. 2 pi r, so r is 4, so it's 8 pi times 1, so the area is increasing at a rate of 8 pi squared centimeters per second. Alright, that one was fairly straightforward. Water is leaking out of a cylindrical tank at 3 cubic feet per second. The radius of the tank is 4 feet. This radius will always be 4 feet, so it is a constant. Alright, so we're looking at volume. We're under the depth of the water changing, so so all the variables are volume, radius, height, radius is going to be equal to 4 no matter what rates that are given. Alright, so the radius of the tank is 4 feet. Depth in water, so the depth, so the height, the rate of the height change. Alright, depth and height are the same. Alright, and what rate did they give us? They gave us the rate that the volume was changing. So we'll go volume of the cylinder. Let me make sure I get this formula right. Volume of the cylinder is the area of a circle times height. Yes. Equals pi r squared times height. R is a constant, so we don't have to worry about the product rule here. So now we get dV dt equals 16 pi dh dt. So plug in what we know. We know that this is 3. It's leaking out, so this is a minus 3. So that height is decreasing by negative 3 over 16 pi feet per second. Let me see my work because I cut you off. So I had this as I took my derivative. I plugged in for A and divided by 16 pi, and there you have it. Alright, the cone is kind of different, because the cone is going to have more variables, but there's a way to make it to one variable. Alright, so every cone has a height. Every cone has a radius. Here I have similar figures. So no matter, or similar triangles. So when I get my depth, I can make a ratio for the height and the radius for this the whole way down. So when I take my volume of the cone, 1/3 pi r squared h, I'm going to have too many variables here. So I need to write one in respects to other. So what are the variables? Radius, the height, 10 inches, 15 inches diameter. And the height is 15. Alright, so okay, we'll get radius later. Okay, so which can remain constant? Well, none of them, because as I fill this up, the radius is going to change, the height's going to change, but it is going to change at the same time. All right, what rate do they want? So they give us the height. The rate of height is increasing 1-2 inches per second. All right. So let's just look down here. If I took the derivative, I'd have the, all right, it wants to know the rate of the volume of the water is changing. So dV dt. So there's our unknown. Alright, so if I differentiate this, then I've got a number for radius. I don't have a number for height yet. I'm going to have the rate of change of the height and the rate of change of radius. It's too many variables. I've got to be able to recognize that if this is 5 and this is 10, then no matter where I'm at, especially down here, so the radius over the height, radius is 5, the height is 15, I'm sorry, not 10, 15. So I'm going to have to plug in, I need to differentiate with respects to the height. So I need to get this as an equation of height and get rid of my r, because we're looking for the height of the water, the rate of the height. So solve this for h. So 5h equals 15r, h equals, solve this for r, I'm sorry, so you can substitute in and get h, get an equation with all h's. So r equals, divide by 15, 1/3 h. So I plug this in down here, and that's going to get rid of one of my variables. R squared is 1/3 height squared times height. Let's simplify it, make it easier. That's going to be 1/9, so that's 127 pi. H squared times h is h cubed. Now I can differentiate dv dt equals pi over 27 h cubed, so that makes that 3h squared dh dt. Alright, let's clean it up a little bit. dv dt, 3 over 27 is pi over 9 h squared dh dt. Alright, so what are we looking for? I need to get rid of this, and this is 1.2. How can I get rid of h squared? Well, it says that the radius is 2 inches, so plug it in up here. So the radius is 2. Multiply by 3, so the height is going to be 6. So I get pi over 9 times 36 times 1.2. So we multiply all this out. 9 over 36 is 4 pi times 1.2. So is that 4.8 pi? Let's do it again. So I plugged in 6 for that. 1.2 here, multiplying all this out, 4.8 pi dv dt. So that is the increase of volume over time as you pour water in at that constant rate. Okay, so we have a ladder leaning against the wall. Ladder's here, base is here, height's here. So the ladder is 25 feet. The base is pulled away. How fast is the ladder moving down the wall? The base of the ladder is 7 feet. So I've got h squared plus b squared equals, the ladder is 25 feet. So we differentiate. This will be the 2h dh dt plus 2b dv dt equals, the derivative of that is 0. So now I've got my rate of change equation. This is height. This is the rate the height's changing over time as I'm walking this ladder away. This is the rate of change over time of the base, this is how long this is getting, and that's the length of the base. So I'm telling you, when the base of the ladder is 7 feet, alright, and I'm also pulling that base away 2 feet per second. And then I want to know how fast the ladder is moving down, how fast that height is changing. The only thing I don't have is the height. But I do have a Pythagorean theorem of 25 at 7 and here. So you set up the equation for that height. So that equals 625, 49, h squared. H squared equals 576. H equals 24. So that's 48. dH dt equals 2 times 7 is 14 times 2 is 28, negative 28. And that equals negative 28 divided by negative 7 over 12. dH dt is negative 7 over 12, and this is feet per second. Alright, so now we're talking about the area of triangles. So the area is going to change as you're going down. So area of a triangle, 1/2 base times height. The area is dA dt plus 1/2. I get, alright, derivative of base is 1 times h dB dt, plus the derivative of h is 1 times b dH dt. And at 7, when the base of the ladder is 7 feet, so this is 7 again, and I want to know the area is changing, so dA dt 1/2. Do I already know the height when I'm 7 feet? Yeah, I found that up here. The height is 24. dB dt, do I know that? Yeah, I'm moving it away, the base at 2 feet per second. And then I know the base is 7. Do I know the decrease of height? Yes, negative 7 over 12. That's 1/2, 24, or excuse me, 48. And that decreases, or that changes, rate of change is 21.958 feet per second. Alright, so find that. Now we're talking angles. Now I want to know the angle is changing from here to here. The base is 9 feet, so I've got sine theta is opposite over hypotenuse. So sine of theta equals 1 over 25 times b. Implicit differentiation gives me cosine theta, d theta dt. So this is the rate of the angle is changing, so this is the rate we're looking for, equals 1 over 25 dB dt. We already know that this is 2 feet per second, so it's 2 over 25 divided by cosine of some angle. How do you find this angle? Well, we're talking about the instant that it is 9 feet. So, sine of theta equals 9 over 25. Theta, therefore, equals sine inverse of 9 over 25. And I'm in radians. It's okay as long as you stay in the same mode, 0.368. So cosine of 0.368. And I'm in radians per second.